So welcome to today's colloquium, and today our colloquium will have maybe a much more applied flavor, I guess, right, than the ones we are used to have. So it's a real pleasure to me to introduce you Professor Pablo Acedo. Pablo works at University of Carlos III in Madrid, right? And he has a group, mainly focused on sensing, sensors, essentially, let's say, classical sensors, but he works, I would say, at the frontier, right, of several fields, including engineering, physics, biochemistry, medicine, several bio stuff, right? So regarding his CV, Pablo has published more than 170 articles in several high-impact journals, right? Well, of course, his group is around 20 people, you said, right? Meaning he has, you can imagine, several projects, including national, European, and so on. And something to which we are not pretty used is the collaboration with different companies, right? So he's currently collaborating with several companies, including Indra, Airbus, and several others, right? And today he's going to talk about from classical to quantum sensors, I mean, his view from this transition. So, yeah, the stage is yours. So, yeah, thanks a lot.
Thank you. Thank you very much, Jorge. Thank you very much, everybody, for coming here. Good morning. As Jorge said, my name is Pablo Acedo, and I have a task here. You know, Jorge told me to talk about this, my vision on this transition from classical to quantum sensors and instruments. I will try to do my best to illustrate this. So, very first view, although Jorge has already said, so I work at the University Carlos III Madrid. I led the sensor and instrumentation system group, and we develop sensors and instruments for different applications: biomedical, environmental, industrial, military applications. Also, is not here, but they told me to, not to tell that. And especially our main focus is in optical spectroscopy, linear and nonlinear, and especially dual-comb spectroscopy. Dual-comb spectroscopy is basically our main field of work. Okay, and since some years now, and also associated to my sabbatical year at the National Institute for Standard and Technologies in Boulder, Colorado, we started this new line on quantum sensors, okay? This is basically the group, so a lot of people here, and some things that what really I want to highlight here that, okay, we do a lot of basic research on spectroscopy and quantum sensors and other kinds of sensors, but also our expertise is focused on taking those sensors actually to the field. So this is one of our first systems that developed for biomedical applications, so for the study of angiogenesis in humanized mice, and this is basically some tissue on chip, skin on chip that is actually instrumentalized to enhance mobility and proliferation of cells, and even we have made things for cars, for engines. This is a radiometer for the Isanya laboratory of the IMET, okay, to measure CO2. And this is a system for mid-infrared spectroscopy that is also deployed in the field. This is another one that to make a hyperspectral imaging. So in the end, we are able to take these things to the lab. And this is something that we will talk about that later. And this is some pictures of our recent effort in the last years on quantum sensors, basically in MV sensor ensembles and also in wide field quantum microscopy that actually in combination with all the collaboration we have with people in cellular biology, and cellular and molecular biology we are doing with them. Okay, so let's start from the very beginning. Let's talk about classical sensors for a while. Where are we? I mean, when we talk about sensing and measurement, so one thing you are really aware of is that nowadays sensor and instrumentation systems are ubiquitous. And when I say ubiquitous, we are not even aware of how many sensors we have. Okay, so we talk about Industry 4.0, but just in your car, in your car there are more than 200 sensors. And some of them really critical. I mean, I don't know whether you're aware that when you're driving in your car, you're driving your car 120 kilometers per hour, 140 kilometers per hour, okay, 40 centimeters from your face, there is a pyrotechnic device, the airbag. The airbag is just an explosive. That explosive system, that pyrotechnic device, is connected to a sensor, to an accelerometer. If that accelerometer goes wrong, I mean, because you brake, because there is something jam or whatever, and there is a bad reading or a misfunction of that sensor, the airbag is going to go off, it's going to explode in your face, and let me tell you, the survival probabilities, when something explodes in your face at 120 kilometers per hour are 0. So your life depends on sensors. And not only, no, of course, biomedical sensors and blah, 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 blah. No, every time you take your car, your life depends on a stupid, MEMS accelerometers, okay? Of course, this is going on and on. Now we talk about everybody has smart watches and wearables. So basically, your vital functions are continuously monitoring, and this is going only to increase, okay? So that's the importance of measuring nowadays, okay? Basically, our lives rely on sensors, not only our wellness or communities or just going home and the lights goes on automatically. Your pure life depends on it. What is the situation now? Classical sensors still are facing a lot of challenges, and those challenges are going to show later on. Also, when we talk about quantum sensors, for example, now we work a lot of sensor fusion, for example, integration of different information from different sensors. Okay, this is an example we did for Airbus Defense and Space, and a plane in a GPS denied and an RF denied scenario that has to rely on internal sensors, for navigation and to go back to its place, based on IMU, International Navigation Units, or combination of, for example, magnetic sensors, mapping the magnetic anomalies in Earth to localize itself, okay? And another very, very important is, for example, the use of advanced signal processing, machine learning and artificial intelligence. This is an example also of our work. These are the millimeter wave spectra of different patients, up to 30 patients, with different hyperglycemic states. And basically here you see nothing. At least I see nothing here, okay? But if you use the proper techniques based on advanced statistics techniques, I just learned that your research vice rector actually collaborates with the lady that is co-author of this paper as well with me, with Carmen. The world is that small, okay? We were able to obtain this pretty linear, relationship between the actual measurements of our spectroscopy system and the reference value that was associated to duplicated hemoglobin 3D analysis. So, a lot of information is, hidden here that can be taken away with this machine learning, artificial intelligence, and there is a lot of things still to be done with classical sensors, using this sensor fusion and advanced signal processing techniques, okay? And this field is evolving, every single day there are new sensors, in the market, new systems, new companies, new startup. It's a multi-billion company. I mean, you can't imagine, the different sensors you have. Only in your cell phone, you have 7 sensors, okay? Just a chip with an accelerometer, gyroscope, and the compass, okay? The camera, and so on and so forth. But there are 2 important things for what we're going to talk about today. We're going to talk today about quantum sensing, isn't it? The most funny thing is that these classical sensors, the classical systems, are really not limited by classical Kramer-Rao lowered bounds. Okay, it's very rare that a system that is limited either by thermal noise, electronic noise, or a shot noise limit, in the case of a spectroscopy. So even, it's not only a problem of signal processing or fusion, there is still room, for classical sensors to improve their sensitivity. I mean, I know very, very few, of the classical sensors that are actually hitting the Johnson's noise limit or the shot noise limit. Okay, so why bother about quantum sensors? Okay, if there is still so much room to improve for classical sensors, so much things to be done. I mean, why now quantum sensors? And this is a question that actually people in my group ask me. Okay, we have a lot of things to do. We have many, many, many projects. Why the hell you are losing time with that? Okay? They asked that 4 years ago, and now they don't ask that anymore. Okay, 5 years ago. I want you to take some perspective. The first thing I always said is that we already, all these classical sensors actually use quantum sensors and devices. The transistor and the lasers both are quantum devices. You need quantum to understand them. You say more or less, but you need some quantum to explain lasers, okay? How do you model spontaneous emission? And this is how a laser starts, okay? You need a spontaneous emission for the laser to begin with. And spontaneous emission from a semi-classical point of view has its weakness, okay? So believe it or not, and also the quantum dots laser, okay? Every laser is a quantum dot laser, okay? And transistors are, born from the first quantum, revolution. And if we see how these devices that appeared, this in the 1950s, this in the early 60s, 1960s, basically they follow this evolution, first scientific understanding done by physicists, technological development, physicists/engineers, and then applications engineers. And I want also to highlight the timeline, okay, at this point. The transistor, 1956, the laser, 1960, the first semiconductor lasers at the ends of the 60s, okay? Yeah. But why now? Why now this buzz about quantum sensors? And there are two things. The first has to do with public relationship. Of course, now we are in the middle of a second quantum revolution, a lot of money going into this thing by the different companies, very important advances, quantum networks, quantum teleportation, the demonstration of quantum supremacy by Google 4 years ago, okay? Of course, to increase the hype 2 years ago, 2022, the Nobel Prize, to Selinger, Aspect, and Clauser, so also put the quantum, on the focus of everything. So now everything is quantum and entanglement and so on and so forth. And believe it or not, this is important for politicians, to put money on the field, okay? So actually there is an actual driving, associated to this hype and these things that most of these effects were well known, a long time ago. Okay, so the work of Aspect is from 1984 or 82, something like that. So we are talking 40 years old, results, okay? And Hohmann experiments and all those things are 30 years ago, 30 years old results, okay? So yeah, but the hype is important, and now there is tons of public funding in the last years, in this, and some companies, even in Spain, Telefonica has a huge effort, especially in quantum communications. Airbus, you wouldn't believe it, especially Airbus in Germany, you wouldn't believe it, the efforts, especially in Embicence and so on of Airbus, Airbus Verica, Resolve, ARC, Technalia here, okay, Sener, a lot of interest, especially on computing and communication. What about sensors? The other thing I want to highlight is that quantum sensors have been also around now for a while, and even commercially, okay? Just think about the SQUID. The SQUID magnetometer, has been around for a while, and you can go and buy from Berkeley, okay? This is a very peculiar result because this reminds me a little bit when I started working in fusion and working in the terahertz range, and the reason why it was needed was there was no classical solution that was able to provide with those sensitivity. Measuring magnetic field with classical waves, with coils and so on and so forth, is extremely insensitive and have a lot of problems. And this was definitely a necessity, and the only answer was quantum, okay? So actually here, quantum showed the actual, capacities to really provide with high precision, high accuracy measurements, okay? But I want to highlight that beyond this hype, beyond this new development and so on and so forth, there are actually very, very important forces that are actually driving this development in quantum sensing, and this is unstoppable, okay? And of course is that the better knowledge of this phenomena like entanglement, coherence, and so on and so forth, the refinement of the experiments, but something very important happened 3-4 years ago. It has to do with the International System of Units, with metrology. I don't know if you are aware, but in 2019, the world changed forever. Yeah, because if I ask you what are the units that define the International System of Units, you will say, well, it's the meter, the second, the kilogram, and so on and so forth. That's not true anymore. In 2019, the meter convention, well, they actually defined the International System of Units completely differently. Now our universe, our world, it's such as this. This is the definition of the International System of Units. Now the meter, the second, the kilogram are not basic units anymore. They are still kept for historical reasons and basically for sentimental reasons. But actually, the International System of Units is that of the unperturbed ground standing perfect transition of decision is this one, the speed of light is this, the Planck's constant is this. These are exact till the last digit. The Boltzmann constant is exact, the Avogadro constant is exact, and of course the lumen, the luminosity constant is this number. As these numbers are exact. And this is a fundamental change. Because this means that if I have an experiment in my lab with enough accuracy to trace any measurement to any of these standards, my measurement is exact. I don't need to go to the Centro Español de Metrología. I don't need to go to the BMP, to the PTB, or the NIST for calibration of my system, because that's what they want to do. I can do the realization of the different units in my lab. Metrology always goes one step ahead of instrumentation and sensing. In 1903, interferometry was just a metrology instrument, okay? Developed by Michelson for some other things. And now we do have interferometers for everything, okay? So when metrologists, when the international system does this step, actually is sending a very important message, because actually this definition of this International System of Units is based on two assumptions: the atomic hypothesis and the quantum hypothesis. Those are now the cornerstone of metrology, or every single measurement you want to do accurately in the world. And now you have a problem with the classical sensors, okay? And of course, they also can be exchanged to information and so on and so forth, okay? Why, the international community does this step? Because, of course, the latest advances in quantum metrology, has allowed to obtain the values for these constants I had mentioned before with enough accuracy to fix it and constant, and relied on the experiments based on quantum, implementations of those results to provide with the basic, units of that. And of course, there is a second step here. This change also allows to what they call this second generation quantum metrology, that basically what it allows is to beat the standard limit in the measurement, that was 1/1, the square root of n, and actually reach the Heisenberg limit, in our measurements. So actually, these are the tools, that, the community is putting for you to do your measurements, okay? We're going to go a little bit. So, as I said, from the metrology point of view, going quantum is not anymore an option. It's just the only way to go. And actually, you only have to go to the Centro Español de Meteorología. We collaborated up with them to see how neighbors they are. And they are hiring people like crazy, 12 people a year, because basically they have to change everything. They need quantum implementation of all the basic units. Okay, we are not there yet. Okay, of course, for the meter, for many years. Okay, of course, for the second, the kilogram is still a problem. The Kibble balance, still has problems, and also the Avogadro project. Okay, so we're still using the stupid cylinder, in the bowl. They are at the same. Still problem with temperature. We need to use ITS 90 still because the single electron transistors are still having problems. But we are almost there, and actually. There are many efforts, especially in the United States. Actually, I don't know if you're familiar with the concept of NIST on chip, NIST on a chip. The NIST, the National Institute for Standard Technology, actually his ultimate objective for the last 50 or 60 years is just provide, the standards in chips. Basically, they can deliver. Okay, so you want the second, here you have an atomic clock, Integrated now, the atomic clock is still this big, based on strontium or ytterbium or whatever, okay? And in 50 years, they're going to give you a chip based on optomechanics, okay, that basically, links KT equal to HF, okay? Because basically that's the whole idea, to link the Boltzmann constant with a frequency, and then you have the temperature, okay? And giving you a chip, okay, with the kilogram, with serialization of based on the watt balance, okay, the Kibble balance, how the kilogram is basically, implemented effect. Okay, so this is a huge driving, okay, because actually showing a way, to people doing classical sensors, okay, how to increase your accuracy, improve your traceability, of your systems, okay? Because basically traceability is not needed anymore, okay? Because you are able to realize to realize the magnitude yourself, okay? And believe it or not, okay, I'm not that far for retirement, so I can live pretty safely with still doing classical sensors, but here there's some very young people. Okay, and we need to think for the future, okay, at this point. Okay, so it seems there are major drivings here, that is pushing ourselves into the field of quantum sensing, and we need to implement quantum sensing and actually do things with them. But we have a very important lessons learned in the first quantum revolution, I say the adoption of the transistor and the laser, and we also have to take that into account when we see how this is going to be implemented. Because from the application point of view, from the industrial point of view, you cannot convince, the different applications, quantum is better than classical, okay? They have other metrics, okay? And from my experience, there are only 3 reasons why a new technology is adopted. The first one is only if this new technology provides with significant improvements over the actual solution. And that's the case of the transistor. The functionality of a transistor was already there, the vacuum tube. Actually, vacuum tubes are much better than transistors. Vacuum tubes are extremely linear over a huge range. And the transistors, believe it or not, they have either an exponential response in the case of bipolar transistor or a quadratic response in the case of MOSFET. So from the point of view of distortion, and signal quality are much worse, okay? But, they were replaced in 10 years because there was significant improvements. The first one is a vacuum tube is this big. Now, in this volume, we can put 2 billion transistors, consuming, 1/10 of the power, the 10 billion transistors compared with a single vacuum tube. Okay, so the functionality was already there. Radios and radar and even TV was already there before the transistor, was invented. Even the computers, there were computers, there was television, there was radio, radar, all sorts of military applications without transistors, but they were adopted because this significant improvement. The second reason is because they provide with capabilities that are not accessible with today's solutions. That was the case of a laser. Okay, of course, we already have light sources before the laser arrived. Okay, mercury lamps, rubidium lamps, they were already there. People doing interferometry for 60 years. When the laser arrived, people was doing Fourier transform infrared spectroscopy, and of course. But suddenly, a light source with a brightness orders of magnitude bigger than any lamp, and with a spectral purity, 7 orders of magnitude better than any thermal lamp, was already available, okay? And, the transition was direct, okay? Because, there is no comparison between, a mercury lamp, and a red laser, at this point. Or there is a third, is the providing of a complete new application of capacity that actually you provide with a functionality that is not there yet. I typically use a sample of the optical frequency comb because I'm a spectroscopy, okay? At that point, linking optical domain with a microwave domain, was done with this change that were realized once a year at the NIST and PTV just because of that. But suddenly, in the 2000, we obtained an optical source that basically was directly traceable to microwaves. And that basically changed, of course, optical clocks forever, but high-resolution spectroscopy, everything, okay? And we are still, there was something that nobody even has thought of, having an optical source that exactly the frequency of that light. And when I say exactly the frequency, it's not that I have a very good optical spectrum analyzer or monochromator and say, no, this is 3.747 wavelength. No. This frequency is 144, 7 digits, terahertz. Exact. Okay? So any of these trees has to be, fulfilled by a technology to actually take on the market, And this is at the point we are now, okay? Trying to identify, a quantum technology that can either provide with scientific improvements of what we have, providing with capacities that are not accessible. That was the case of the squid. That was the case of the squid, okay? That there was no classical counterpart to measure that very small magnetic fields. Or actually that there are capacities that basically, they were not there, and suddenly they are, and we can do things with them. Okay? Be careful with the hype. This is my favorite and most important graph here. I'm old enough to have lived through many, many hype cycles of different technologies, okay? And quantum technology, especially sensor, is sometimes oversold. And they are mainly oversold by physicists, and it's not their fault, okay? It's a problem that to build actually a system, building sensors and take a sensor to the market, is difficult. And some claims that are made, and I'm going to talk a little bit about this during the talk myself, are a little bit problematic. I will talk about that later. And this is a quote I can remember from him that said that we cannot sell quantum sensing as a hammer that turns the problem into a nail, okay? Sometimes, we have to be careful with that. Okay, I'm going to fly over these graphs, the quantum sensor definition characteristic, but I really want to make clear what we understand about the quantum sensors, okay? A quantum sensor, is typically used to describe a quantum, when we use a quantum object to measure a physical quantity. Typically, it's going to be a qubit, okay? So there's a quantum object, there's a qubit, and we need to have coherent control over that qubit, This is what defines quantum sensing, the coherent control of a qubit. We can also talk about quantum sensing when we have the use of quantum coherence. Every time you use quantum coherence, we are talking about quantum sensing, okay, because that's the biggest difference with classical sensing, or we are using quantum and entanglement, okay? Generally, okay, a quantum sensor, is described because it has the following attributes, okay? Typically, we have a system that has two discrete resolvable energy levels, okay? This is a generalization, okay? We can also think of photons, for example, and polarization, but I'm just doing this general, just to have the same language. So we have these two levels with a given energy or with a given probability of transitions. It's important in a quantum sensor that we should be able to initialize the quantum system in a well-known state, and we should be able to read out the final state. As I said before, the quantum system can be coherently manipulated, okay, typically by time-dependent field, okay? And the most important thing is this: the quantum system interacts with a relevant physical quantity, and that interaction is quantified by a coupling or transaction parameter associated to the interaction Hamiltonian. You are familiar with this. That is basically the sensitivity of the sensor. This is the most important thing, because what we are doing here is that we are taking advantage of actually the weaknesses of quantum systems that they are actually pretty weak, and they have a coherence that is short, and they are very sensitive to the environment, to use that high sensitivity to the environment in our advantage to make a measurement, okay? But this has a problem. We have to really isolate that interaction and to make sure that this interaction is associated only, as I said, to the parameter of interest, and there are no cross sensitivity to other parameters. That may be difficult, in quantum sensors. Okay. Why I wanted to discuss these 4 points to describe a quantum sensor? Because not everything that people claim is a quantum sensor is a quantum sensor. And I always like to make the differentiation between quantum sensing and quantum detection. When I talk about quantum sensing is, when I'm able, to initialize my quantum system. I have a quantum system with 2 system levels, or a photon with 2 polarization. I'm able to control coherently the interaction and so on and so forth, okay? And typically it's associated with parameter estimation and all the techniques, the different models and so on and so forth, and you use quantum estimation theory, and you take advantage of quantum objects and systems to measure with unprecedented resolution. That's the important. And basically, your object is to measure with 1 over n, with a Heisenberg's limit. That's a quantum sensor. That's quantum sensing. A quantum detector, okay, a quantum detection is when you actually use quantum phenomena, but in a classical system. The typical example is a single photon counter, a superconducting nanowire. Of course, superconducting nanowire, relays on you need a quantum model, and you have the tunneling and so on and so forth. But at the end of the day, that this superconducting nanowire single photon detector is just counting photons, and you are limited by the actual statistics of the field. There is a Poisson distribution, the shot noise is 1 over the square root of n, okay? So you are using a quantum detector in a classical sensing system. Everybody's following me here? Okay? Of course, it's a quantum detector, as is a photodiode, if you want to ask like that. But the photodiode, you generating a current, you are not clicking the photons, So be careful. Be careful with that. Of course, we use single photon counting detectors, SPATs, in quantum sensing experiments, of course, but the quantum sensing behavior is not associated to the use of a single photon counter. It's associated to the actual system, either it is an NV, of trapped ions, or whatever system you have. Okay? So I want to really draw this line here. I want to somehow escape this because I'm sure you're familiar with this. If not, you can come back to me. What is a typical quantum sensing protocol? Okay, because these are typically a generalized quantum sensing protocol that is associated to quantum sensing. And I'm going to go to actually examples of implementations of quantum sensors. Okay, this is a very extensive but different proof of concepts, of quantum sensing using neutral atoms, trapped ions, Rydberg atoms, solid-state spins like MV centers, of NMR, superconducting circuits, squids, elementary particles, single electron transistors, and optomechanics to measure temperature, and of course interferometers. Interferometer, you may say, is pretty much classic, okay, but if you want to convert an interferometer into a quantum sensor, you just put one photon at the input, and basically you have an automatic quantum sensor, okay? Yeah. So interferometry is something that is in the middle, because you can do a lot of things quantum with interferometer, okay? And as I said before, not only this proof of concepts we have it, we already have quantum sensors in the markets. For example, this gravimeter, for muquas, that actually is a pure quantum. Basically, you just send up cold atoms. You allow them just to fall by gravity. You initialize them with a pulse, and then you read them out. Okay, and this is how you measure gravity. It's a pure quantum sensor. You have all the steps that I mentioned before, but I didn't have permission to go through. But you have initialization, coherent control, and projection and readout. And you can buy this if you have some 100,000 euros, of course, because it's extremely expensive. But it's for geodesy application, oil and gas industries, and they have tons of money, so they can use that. Okay, and also not only absolute gravitometry, but also radiometry can be measured. Of course, you are familiar with NMR, nuclear magnetic resonance, is also a pure quantum, sensor. You just put the magnetic field, you have the position of the nucleus, you have measure the projection. Okay, and this has been also around for many time, and actually is the workhorse in some parts of material science, again, because they are providing with the solution beyond any classical counterpart. There is no classical solution to this problem. Okay, these are not in the market yet, but very soon near you. And when I say near you, I say in satellites. But basically, this I like this picture. This is from a talk by Scott Didams in the year 2000 in San Diego. This is how disruption looks like, okay? This is the uncertainty of optical clocks. This is a logarithmic scale, and you know what happened here, the optical frequency clock, okay? The comb, the optical frequency comb happened here. And you see directly in 5 years, 2 orders of magnitude, okay? And this has gone down to the -18 here, okay? And here is the Nobel Prize for Hatch and Ho, okay? And this is a disruption, a quantum disruption here, okay? Of course, in a niche that is not so well known as is optical clocks, okay? But, and improving accuracy in 2 orders of magnitude or 3 orders of magnitude in 5 years is something that is very rare in the history of humankind, I would say. Okay, it's incredible. Optomechanics already demonstrated, not in the market, but let's hope also close to you. And there is another important thing I want to highlight, that is the quantum enhancement of classical sensors. The example is LIGO. okay? Sometimes we can have a classical sensor, in this case an interferometer, and enhance it using quantum techniques. In this case was the use of a squeeze vacuum, introducing the dark port of the interferometer just to reduce the shot noise in the measurements. Now this is regularly working in LIGO, with a squeeze between 6 to 10 dB, I think they are now, and basically that goes directly to your shot noise, and that improves, a 10 dB, it's an order of magnitude increase, or decrease basically in your noise flow, okay? And that goes from detecting a gravitational wave once in a while, as at the very beginning, and now that I think they are detecting every month, or every week, they are detecting, gravitational waves events, in LIGO, BIGO, and so on and so forth, okay? But the real point of my talk is not this. I'm going to describe a little bit MV centers in detail, and we are going to move this. How many of you are familiar with MV centers and quantum sensors? I know many of you, so please raise your hand. Yeah? So you are familiar with MV centers? Okay, so for the 50% of you, but this is an MV center, okay? Basically, it's a defect in a crystalline structure, in this case in diamonds, so a carbon is substituted by a nitrogen, and then we have a vacancy. And this, you ask Jorge, and it tells you that it works, can be modeled like a two-level system, okay, and that has this ground state configuration. It's triplet state, that they have this separation, that's 2.87 gigahertz, and here we have this degenerative MS plus minus 1 state that can be further split using Siemens with a magnetic field, and you have this separation, and this basically, comply with all the requirements we asked before for a quantum sensor, okay? So it's a system with clearly energy levels that are differentiated, that we can coherently, control, that we can initialize easily, and we can read out easily, okay? Using green light and red light and so on and so forth. Again, if you have questions, you can ask Jorge or people of his group, but the important thing here is based on that Siemens splitting between the MS plus 1 and MS minus 1 event, we can read out a magnetic field, and basically this stripping the microwave frequency and just reading the fluorescence, associated of these transitions. The transition is, this emits, and this does not emit. Just measuring this frequency difference, we are able to obtain the value of the magnetic field along the axis of the defect, just using these numbers. And this relates exactly with what I said at the very beginning about this forcing of the new international system of units, and so on and so forth. All these numbers here are constants, are universal constant. Then there is no calibration needed here at all. This is exact. These are constant as far as we know, until next physics, shows up that tell us that no, the alpha, the geomagnetic ratio of the electron is not constant, but that will be a real breakthrough in physics. Until then, those are constants. And the Planck's constant is constant, but constant until the last digit. And that happened in 2019, not that long ago, okay? Until 2019, the Planck's constant has some uncertainty associated to it, because what was exact was the meter. Not the meter is nothing. What is exact is the Planck's constant and the speed of light. As I said, this is a change of paradigm that you have to really interiorize to understand where we're going to. And of course, just measuring these frequencies, we can obtain directly the value of this field. Of course, you can ask, okay, but I need to measure frequencies. How do I measure frequencies? Measuring frequencies is no problem. The best thing humankind does is to measure time and frequencies, okay? A 16-euro Casio watch has a short time uncertainty of 10 to the minus 5 measuring time. Okay, that is better than any temperature sensor you may find in the market. But if you have a remedial clock disciplined with GPS, 3,000, 4,000 euros in your lab, you have 10 to the minus 11. Okay, 11 digits. 11 digits. Okay. Of course, if you have access to an optical clock or to a session standard and so on and so forth, that goes to 10 to the minus 14, 10 to the minus 15, 10 to the minus 18. 10 to the minus 18 is measuring with milliseconds accuracy the age of the universe, just in case you wonder. Okay? So this is the actual characteristics of a quantum sensor. I don't need to calibrate my system. I don't need that every year send my thing to Agilent or Keysight for further calibration. That chain is broken. That chain is broken. Of course, this measurement has to be done with the proper uncertainty, and you have to know how to do that, and to know how to do the statistics. Of course, how to evaluate the uncertainty. Okay, there are some techniques here, but there are well-known techniques for people that are doing sensors and people that do instruments. Okay, and of course you're using MB centers. You can do vector magnetometry because you have the sense the defects in 4 different orientations, and of course you have in the end 8 peaks, and you can measure multi-parameter sensing possible, and you do different non-linear spectra, and you have different measurements protocol. I'm actually going fast through these view graphs because I assume you are familiar with this, and if not, you can ask them. Because the point of my talk is not this. It's not to talk about the particularity of quantum sensors. My task here is another one, as you will see later. Okay, we can use this view graph is good because, for example, MB centers are very versatile. You have different protocols that you can use depending on what you're actually looking for, continuous wave, pulse, you can use hand echo, you can use dynamical decoupling, you can use advanced pulse sequences as Jorge and his group are designing. You can do many of these, and let me tell you, there have been tons of concepts of the use of ambient sensors to measuring single neuron action potentials, to measure, this is wide field microscopy. This is something that we also doing in our lab. We are doing wide field magnetometry with diamonds, so you can have a 2D image of biomagnetism, and you can have magnetocardiography using MB centers. So here you have your poor animal, and you can measure this, and you can even put together a gyroscope, or to do detect reactive oxygen species. Hey, that's it. So we have a system, we have MB sensors that they are able to measure magnetic fields and also force and different things, and we have demonstrated we can measure things with rats. That is always very spectacular. Okay, I also do rats. In my life I have killed around 400 rats, in my experiments. Not that proud of that. Okay, and we have made gyroscopes, and the problem is solved. My ass. No. We are not even close. What we have seen in all these samples, and all these samples you've seen in the literature, are proof of concepts. And let me tell you, in most of the proofs of concepts, the actual performances in terms of accuracy, stability, and so on and so forth are well below the actual, characteristics of classical sensors. I can measure this, action potential much better with 3 different sensors. Classical. Magnetocardiography of a rat. Those signals I can recover with my smartwatch here. And well, the gyro isn't doing not that much, okay? But let me tell you, these guys have not compared themselves with the actual gyroscope the military people have. Okay, you wouldn't believe it. So, the trick here is that we don't need sensors. We need instruments to really not only go to the market. I'm not talking about putting together a company and make yourself rich. I'm just using these things to actual things. And what you actually need is something like this. This is one instrument we actually did for La Paz, actually for the people of experimental surgery, okay, the people. And this is a very stupid instrument. What was difficult? We just put this into a cage and put these things here, because in the end, here you have it in the operation room. Because the patient, the rat, the cell, is not going to go to your lab. You have to take your system where the problem is. And actually, I'm not even allowed into the operation room. Here is Luis Ojeda. I'm going to introduce you to this guy. Here is the patient. Here is your instrument. And you can see here the optical fiber that goes here. I don't think this is not very well looking. Okay, but you see here the optical fiber just here and going down, you know, and helping this guy saying if the anastomosis is properly done, you know, in this reconstructive surgery process. Okay, and there is where we want our quantum sensors. And the funny thing is that this thing is operated by this guy. You know, you cannot go there and say, no, wait. I'm sorry, my bad. No, I'm pressing the button. I'm aligning this thing for you. The surgery is not going to stop for you. And it has to be operated by that guy, okay? And this is where we need to go. We need to improve the actual characteristics of the sensors. Actually, we need to actually benchmark our sensors with the best classical sensor, because typically now benchmarking is doing with the previous. Okay, my MB sensor, my system is better than the one that was published the year before. So my sensitivity is 1 nanotesla per square root of hertz. That is better than that guy that published this last year before. Okay, will you please benchmark that sensitivity, not with the guy that published, with your friend that published the day before with exactly the same system, with all the systems that are in the market that can do exactly the same? That's the first thing we have to do. Of course, we need to optimize the components to make compact systems, or at least with the same compatible with the intended application, and to improve difference in system operation. And actually, that also involves many, many things. The first thing it means is to create an ecosystem, a complete ecosystem that is able to provide with fabrication, functionalization, and so on and so forth, okay, that actually can provide with that. And actually to, you know, improve things. This is things that we are doing in the lab. For example, optimizing the antennas, optimizing the packaging, optimizing the actual reading, you know, techniques to improve the frequency, the accuracy and resolution, to reduce the times, and so on and so forth. And as Jorge is becoming to start nervous, I'm going to finish, okay, because I have just 5 minutes. Only 2 viewers for you. As a brief abstract, please be aware that quantum sensor systems have been amongst us for many years. This is something we sometimes overlook, but there has been around, okay? It's nothing completely new. What is actually new is that now we are actually starting to try to compete with classical sensors. Until today, only quantum sensing like squids and gravimeter were used when there was no other option. It's like terahertz in the 80s. You know, terahertz were used only in radio astronomy and in plasma fusion experiments. It was one of those, because they were the only 2 fields, you know, when there are all the other wavelengths that can be used. And we have to do terahertz, you know, and, you know, for fusion plasma experiments. And at some point, they say, okay, we are moving away from those niche, And that is what is quantum sensors do now. Okay, we are going away from that, and we are now trying to compete with classical sensors, with classical measurements, because we have clear advantages and we can do that. That's the big difference, okay? And this is what have changed in the last year. But not only that, there are very important forces that are driving that, and those are important. Of course, one major driving force is, besides the funding of the government and the company, is because, the field is mature. The experiments are well refined, are very well understood, okay? They are repetitive. People, the knowledge is spread around, okay? And also, not overlook the importance of that change in the definition of the international system of units as what metrologies are going through. And they are pushing really hard in that direction. But again, for this system to really have a clear societal and economic impact, several additional advances are needed, especially for the point of view of system sensor optimization, identification of areas, market understanding research, proper exploitation, companies, and using, and some humility, to actually benchmark your systems with what is actually out there. And that starts, learning about what is out there. And you have an advantage in quantum sensing, is that for many, many years, people in classical sensor have developed additional and very powerful techniques to really lower the sensitivity levels. Statistical techniques, artificial intelligence, sensor fusion, strategies and architectures, okay? And all of those things are there for you to bring them to the quantum field, if you know them. But there's tons of tools that can be used. And my last view graph, what lies ahead? In red, my personal view. This is my opinion, I'm the only one to blame. Quantum technologies are here to stay. There is, no doubt about that. Even though I'm a classical engineer, that did my bachelor in the last century and so on and so forth, this is here to stay. But there's no other way. At some point, it's going to show up. Just look what happens in metrology. What I do expect in the near future, I expect two major outcomes. I expect a potential major disruption, but probably in computing or communication. Probably quantum key distribution is going to produce a major disruption in the near future. Just talk the banks, just talk Telefonica about that. So there's going to be a major disruption, but there is another outcome, a steady and increasing incorporation of the technologies in different applications. So there is going to be, steady. At the very beginning, it's going to be niche markets. They're going to spread somehow in combination with classical sensors. Sensor fusion is there, okay? And I expect this not in the near future. This is happening now. And what is my long-term vision? My long-term vision is that eventually the use and exploitation of these concepts will be as natural as using a laser or a transistor it is now, right now. The program I studied in my school was designed in 1962, okay? So that was the program I studied, 1962. Okay, and at those times the transistor was studied as a quantum device, okay? And Ebers-Molls equations, the whole Ebers-Molls equation to understand the transistor and so on and so forth. Now, my kid use Arduino, in school, okay? And asking about the Ebers-Molls equation, okay? So that's the long-term future. And they will be just there. We are seeing that in the programs. Now quantum is even taught in some engineering degrees, okay? Like in our school, we are teaching quantum at engineering level, not anymore a master level, okay? And that's how it's going to happen. With that, thank you very, very much. Hope you have interest on this. And if you have any questions or details or whatever, open to anything. Thank you very, very, very much.
Okay, so we have some little minutes for questions. Any?
So thank you very much for a very interesting talk, for the passion that you transmit.
Cool.
And so I have a question, a curiosity about this, the device that was used in the surgery room, what was about?
Excuse me, which device?
That was used with the surgery.
Yeah.
What was doing in particular the device? What is it used for?
Well, this is a problem in reconstructive surgery. Okay, basically this guy usually work in the breast reconstruction as a mastectomy. Okay, so it's a very important problem because when you do is you remove the breast of the patient, and basically you take with this a flap. A flap is a piece of sane, tissue that you take typically from the abdomen of the women, because that's not for men, and you put in the breast. The problem there is that you have to perform perfectly the anastomosis, just basically to connect well the arteria and the vein. Okay. Typically, the connection of the arteria is very easily even a simple, just by side, you just press the thing and you see if there is probably perfusion, but the return is the problem. Sometimes it's not properly seen. And the problem is that you remove the surgery and the return of the blood is not properly used. You have basically a problem that when you see it, it's typically very late. And basically you have to remove and to perform another surgery. And that has a very important impact in the patient, in the women, because you have the two things. Basically, that woman is not able to wear a bikini never again in her life, because it has been removed from here, but now you have to remove another part. And psychologically and medically, it's a very impacting the women. So that system was actually looking for actually the total hemoglobin content, in the whole tissue to see if there was accumulation of blood associated for about anastomosis in the breast. So that was the clinical scenario. That's something I don't have time here to discuss, but when you actually take these things to the field or to the market or to solve difficult problems, the first thing you have to do is to learn about actually the problem, and especially talking to doctors is difficult, but sometimes you get a master on reconstructive surgery or whatever, and actually that's what I do for a living. Actually, I'm not that good at anything, but I'm good talking to doctors, to biologists, to people doing defense, and when they want to kill a lot of people or not to be killed. Actually, my work is trying the planes not to be destroyed. That's my business sometimes. And yeah, you have to talk to them and actually identify the problem. And you will think, okay, that seems a pretty simple problem. There is no solution for that. I mean, how the hell? And there are the world is full of problems that and how do you do normally? We just go every 2 hours. We just look at this and it looks okay, and we just cover it back again. So that's the standard procedure. Okay, I think we can do better. So that was the actual instrument and the actual demonstration.
Okay, thank you.
Okay, maybe one additional question in case there is. I don't see hands. Okay, in any case, Pablo is going to be with us the whole day, right? Leaving quite late today, so yeah.
Yeah, well, I didn't pay much attention to the actual details of MB sensors and all the quantum part because I understand you are the experts here. So that's why I prepared this talk, from this other vision. This vision from a guy doing sensor for the classical. And so you have the complete picture and how I see the future that I think is bright for you, let me tell you. Not so bright for people still doing string gauges at this point. Very classical sensor, if you know what they are. Okay?
Good. So if no more questions, we can thank Pablo again.